Hello students, welcome back. Let's have some discussions on optional topics. Sections 5 and 6 that is. Probably in 2 separate videos, possibly more. Okay, let's begin. Section 5, face portrait. Before giving you the definition of the face portrait, let me give you some visualization first. Let's have some naive understanding first before going over to the definition. Here are a couple of examples of face portraits. The first face portrait here corresponds to the first system, which I'm highlighting in blue. And the second system here, the second system here, which I just highlighted in green, is associated to the second face portrait here. Now, let us analyze these face portraits and then let's check out some behavior here. Looks like we have the origin here, also there at the center. And then it looks like we have some parabolic curves, and then looks like points are moving away from the origin following these parabolic curves. Do you see these arrows here? Arrows are outward. So points are actually moving away from the origin, it appears. And the same thing is going on here as well. Do you see that kind of behavior? Basically, that's what face portraits do. The purpose of the face portrait is to convey the qualitative behavior of the systems, especially the homogeneous systems of first-order linear ODEs, in brief and concise form, but still accurate. So this is tall order, brief and concise yet accurate. It's a tall order, but in any case, we saw a couple of examples. Here are another couple of examples. The first one here is associated to the first system here, which I'm highlighting in blue, and the second picture, second face portrait, is associated to the second system, which I just highlighted in green. Let's analyze these face portraits. Looks like we have some rotation going on here, counterclockwise rotation, but at the same time, the points are spiraling inward toward the origin, and same thing is going on here. But this time we have circular rotation for the first picture. Here we have elliptical rotation, but in any case, counterclockwise and spiraling in. Still, it appears that these two are intimately related. After all, both are same direction in terms of rotation and then spiraling in. So are they related? Maybe they are the same. Maybe we are looking at the same system in a different viewpoint. Start from here, from the left-hand side, and tilt it a little bit and look at it sideways. Maybe you're going to get this. Is that really the case? The answer will turn out to be yes, they are related. And same goes over here. This is a standard picture, and then tilt it a little bit and you're going to get this. Okay, we went through some examples of face portraits and then we discussed its purpose, the purpose of face portrait. That is, we want to describe the behavior of the original homogeneous linear system briefly and concisely, yet accurately. So, what is it? Okay, here's the definition, and let's start from a homogeneous system of first-order linear ODEs like this. Here's the system of ODEs, and we have an initial condition, and based upon these, you're going to get this formula. That's the solution formula. Now, instead of looking at this formula as the analytical formula of the solution, look at this expression as, especially this expression here, geometrically. So what do you mean by geometrically? Well, this is a vector function, so it's an n-tuple of real functions. Now, it's an n-tuple, so fix my t-value, then we're going to get an n-tuple of real numbers. So we can put it in an n-dimensional Euclidean space. Special case, if you have only two components, then you can put it into two-dimensional Euclidean plane. it's a lot easier to visualize two-dimension, as you saw in these kind of examples. So most of the visualizations and examples here in this section will be two-dimension, but that's for easier visualization. Theoretically, we can go arbitrary and dimensional case. Now, a single point z of t for fixed t is not that interesting because it's just one point. So what we're going to do is to move it around, move t around. So a point z of t is moving around as t moves from t1 to t2. We get a solution set, not just a point, but a solution set given by this vector function z of t, where t is moving from t1 to t2. That kind of thing is called a trajectory or an orbit. And by the way, that Euclidean space that we started is called the phase space. Why is it called phase space? That's because the phase space that we are dealing with, these n-dimensional spaces, usually come from measurements, and we have various measurements and put those two or all those together, and that's how we get those space. It's not the physical space that actual particles are moving around, in which case we cannot get anything more than 3. But phase space, because it's coming from various different kinds of measurement, you can easily have some 1,000 dimensional spaces and things like those. And that kind of things are called phase space, special case for 2D, phase plane. And then the solution set, where t is moving from t1 to t2, is called a trajectory or orbit. By the way, way back in lesson 1b, in week 1, I used the term solution curve. And the trajectory and solution curve actually mean the same thing, and also the orbit in this case. You see, z of t is a vector function. Z of t is a vector function, and for each t, each fixed t is a point, and this is continuous. So that point is moving around continuously in the space, so it's a curve. If the point is moving around discontinuously here and there, then it's not a curve. We may have some curved segments here and there, but we lose our control quickly. But if it's continuous, it's a curve. But it's actually better than just a curve, because this is a solution of a linear ODE. It's differentiable arbitrarily many times, so it's a smooth curve. That kind of thing we call it trajectory or orbit. Earlier, we used to use the term solution curves associated to the direction fields, but it's historical. It's traditionally the solution curves are used in that environment, and with phase portrait, historically people use trajectory or orbit. And orbit is a little bit more inclusive term. We use the same term orbit when this z of t is jumping around as well. But trajectory, that is for continuous and smooth curves only. Now, a graph around the origin, which we call the equilibrium, by the way, again from the historical reason, and that the graph around the origin that shows a number of trajectories given by different initial points is called a phase portrait. Let's go back to the example here. So we select some initial points around the origin. If I select this initial point around here, where my mouse is running around, then from here we'll follow this trajectory B, and then the point will move out, and so on and so forth. Repeat that several times around the origin, then you're going to get this phase portrait. Similar thing here. If I happen to select a point around here where my mouse is, then I'm going to follow this trajectory D and move away from the origin from the second picture, and repeat that several times around the origin circularly like that, and you're going to get the phase portrait. The key is not to put too many. If you put too many, then you can't really understand anything. If you put too few, then again you lose information. So it's a balancing act. These kind of pictures are actually perfect. Brief, concise, yet accurate. One more thing here. Why is this called equilibrium, the origin? The reason is if you put in this z is equal to 0 vector, then 0 vector times a is also 0, so z prime is also 0. What does that mean? From the origin, if I have a stationary point, then velocity is also 0, so that point is not moving. So if I'm precisely at the origin, it's not moving. That's why it is called equilibrium. But that equilibrium is unstable here, because if I'm precisely at the origin, I'm not moving, but if just a small wind knocked me a little bit, then I'm going to have to follow appropriate trajectories and blow away. So this is highly unstable case. If all those arrows are moving inward the origin, then it's stable. And here are some examples of stable equilibria. Here in the origin, points around the origin are spiraling inward, so this is stable. That too is stable. Okay, we went through a lot of terms. Phase space, phase plane for 2D, trajectory or orbit, equilibrium, phase portrait. We went through a lot of terms. And then, did I make a guess whether these two are related or even identical? Same for these. Let's answer that question. And that's called the affine equivalence. We say two coordinate systems x and y are affine equivalent if there's an invertible matrix such that x can be written as py like this. This matrix P is called a transition matrix. What does that mean? If that happens, that means we're basically changing the viewpoint. And if two coordinate systems are related like this, then the matrices A and B, A which is blue and B which are green, are related like this. B is P inverse AP, or maybe vice versa. If that happens, we say A and B are similar. And then if A and B are similar, then you can make an interesting observation here. If these are similar, how about A squared and B squared? B squared is basically P inverse AP, but then again another B, so P inverse AP, that's it, isn't it? But then again, matrix multiplication is not commutative, but it is associative. So we can calculate this first, and P inverse, that's identity matrix, so that goes away, and A times A, so that's A squared, and what do we have? A squared and B squared are similar. And if I repeat it many times, then I'm going to get arbitrary power. B to the k power and A to the k power are similar. And then apply that to the Taylor-Maclaurin series expansion of this exponential. Then you're going to get matrix exponential can be written as P inverse matrix exponential like this. So matrix exponentials are similar as well. You can easily deduce that. The detail is left to the students. It turns out that the systems we saw before are affine equivalent. This blue system here is associated to this. This green system is associated to the second. And then it turns out they are affine equivalent. Turns out you can find out the transition matrix like this. So the blue matrix is P inverse, green matrix P like that. So these two are actually the same picture, just tilted, and we are taking different viewpoint. That's basically it. That's why they resembled each other. How about the next example here? It turns out like this. This blue system here is similar to the green system here because the coordinate systems are actually affine equivalent. So this blue is equivalent to P inverse green P. So these two matrices, blue and green matrices, are similar. That's because the coordinate systems, UV coordinate and XY coordinate, are affine equivalent. Not surprisingly, we are looking at the same qualitative behavior, just tilted viewpoint. Now, in terms of this affine equivalence, it is possible to classify the behavior of the first-order homogeneous linear ODEs, and that's called Jordan canonical forms, and it is done in terms of eigenvalues. If you have two different eigenvalues, for higher dimension, the eigenvalues are all different, call it hyperbolic. And it's this kind of circumstance. Let's see. One eigenvalue is greater than 0. Both eigenvalues are greater than 0. One eigenvalue is negative, one eigenvalue is positive. Both eigenvalues are negative. What's happening here? Let's see. The matrix is similar to this matrix, lambda 1, 0, 0, lambda 2, and lambda 1 and lambda 2, those are two different eigenvalues, all right? But depending upon signs, we have different behaviors. That's going to be answered by this. E to the at power can be written as, by Fulmer's method, e to the lambda 1t times matrix, e to the lambda t to t times the coefficient matrix, like that. Remember, Fulmer's method. And e to the lambda t, why is it related? Because e to the lambda t times appropriate initial vector, that's going to give me the trajectory. So this one is constant. If this is getting bigger and bigger and bigger and bigger and bigger, that means z of t is getting bigger in absolute value. It's moving away from the origin, and vice versa. And that's the first circumstance. Lambda is greater than 0. Then as t gets larger and larger and larger, as time progresses, this is getting larger and larger and larger. This 2 is getting larger and larger and larger. So either direction, u direction, v direction, or x direction, y direction, both are dispersing away from the origin. In this case, the third case, both are decreasing. So x direction, y direction, decrease, decrease, and everything is converging into the origin. Unstable versus stable. The center part in the middle part, one direction dispersing away, another direction merging in. So in x direction, merging into the origin, because lambda t, e to the lambda t is getting smaller, smaller, smaller towards 0. But in vertical direction, moving away. So basically we follow these hyperbolic paths, and that's the reason why this system, this circumstance, is called hyperbolic. And these pictures look more like parabolic, but we don't call those parabolic. It's called hyperbolic. And the reason, this is far more dominant in practical circumstance. What if you have 100 eigenvalues? This one is talking about all positive, all 100 positive. Here, this one is talking about all 100 eigenvalues are negative. How likely are those? This one, some positive, some negative. So probabilistically, this is far more likely than any of those in real life circumstance. So whenever you have different eigenvalues, most of the time you're going to get hyperbolic picture like this. That's why it is called hyperbolic case. That's J1. I'm kind of running out of time, so I'll have to discuss the other cases, J2, J3, J4, and so on in separate videos. So I'll have to stop here. Sorry about that.